Hello everybody and welcome back. We're going to be covering the topic of electronic steering assist systems, and we briefly touched on some of this in the steering columns and gears with the electronic power steering column and the electronic power steering gear as examples for how some manufacturers accomplish this. Newer systems on more recent vehicles are more likely to have electrified systems. Previously, manufacturers were using hydraulic power steering only, and as the phase shifted into the electronic or the electrified system, there was sometimes a hybrid of hydraulic and electric power steering assist. The first one we're going to cover is variable steering assist, using an electronic motor to restrict and allow more flow of power steering fluid on a hydraulic system. On a hydraulic system, a power steering pump is outputting fluid pressure into the system. That output fluid pressure can flow through a valve assembly that's controlled by an electronic armature. So as the armature rotates, it may move in and out and close a valve and open a valve with a pintle. As the motor restricts flow through the orifice, the excess pressure can then loop back around to the return side and be routed back into the reservoir. During the driver's steering input at the wheel, the steering effort off of center, left and right, may be more restricted to allow less power steering assist from the system. This would be effective when the driver is making subtle changes to the steering angle, like when traveling at higher speeds on the freeway, or just light maneuvers around town. There isn't much steering assist needed to move off of center just a little bit. So as the system may restrict fluid pressure to the assist system, that would allow the steering to feel a little more heavy right off of center or at higher speeds. Wouldn't be as easy to steer the vehicle at higher speeds for stability reasons and for feedback to the driver. Then at more extreme angles, that variable steering assist would back that armature out, and that pintle would allow more fluid through, and the steering effort would become more easy on the driver, and the steering system would be providing more steering assist. Another way to accomplish variable assist with a hydraulic system is, instead of having a belt-driven mechanical pump, is by using an electronic controlled pump. So with an electric motor generating power steering pressure, instead of this being constantly spun at the engine RPM by a serpentine belt or other method, the electronic power steering pump assembly may be able to regulate how much pressure it's putting out and increase or decrease based off of driver input and demand, which would then not require the use of a valve to restrict the flow of the fluid. That's more of a design that's going to be used with a mechanical pump, because it is always turning with the speed of the engine, whatever the speed of the engine is. So that output is going to be coming out from the pump regardless of driver input, and it has to be looped around back to the reservoir and recirculate the fluid. With an electronic powered pump, there's no need to have it outputting a pressure at all times. It can be more on demand and regulate the power steering assist available based off of the driver's input. Another added benefit for an electro-hydraulic power steering pump, again not driven by a belt by the engine, but driven by an electric motor, is it can be mounted in a number of different locations around the chassis of the vehicle for conserving space or reducing costs in manufacturing process for where it is going to be located. Now, with that in mind, it doesn't mean it's going to be easier to service that system from a technician standpoint. It just means that manufacturing the vehicle may be a little faster on the assembly line, shaving off a minute or two on the assembly line process, and over 1 million cars, the manufacturer saves a substantial amount of money. But keep in mind, manufacturers are thinking about cost of manufacturing, not what it's going to cost the service of the vehicle in the future. So electro-hydraulic power steering systems may be located in places like the fender well, or down behind the engine, or in the front area of the chassis near the core support. So reference service information to know exactly how and where to service the system and if there are any safety precautions. Fully electronic power steering systems that use no fluid at all, so there is no hydraulic system involved, are going to likely be using a torsion bar connected to the steering column. It may be at the steering column, it may be at the steering gear. but typically there will be a torsion bar that allows movement between different coils or excitation coils and position coils to monitor which direction the driver's input is going and to determine how much torque is being put on the steering at that time. The more torque, the more assist is needed. So it senses direction and the amount of torque. Excitation coils are going to be very similar to tone rings or reluctor wheels. These can be of a few different types of design. There may be 3 of them per sensor assembly. Oftentimes, the sensor assembly is not able to be serviced separately from the steering column or the steering gear and would require replacement of the entire steering column or the entire steering gear assembly. On a fully electric power steering rack or steering gear, the sensor in the input portion of the pinion gear is going to detect the direction and how much effort the driver is inputting into the steering of the vehicle in order to determine how much assist to provide. Then that input is going to a control module, which in this case is right here, and the control module is going to output an amperage to the electronic power steering motor itself. That motor will turn and assist the rack in whichever direction the driver is intending. Again, we can have variable steering assist. So at higher speeds, we will have less assist, and at lower speeds, we'll have more assist. On the Chevy Cobalt steering column example, the electric motor and electric power steering assist is incorporated into the column assembly, and there is no electronic assist beyond the column. So everything from the base of the column through the intermediate shaft and into the steering rack is fully manual. The assist occurs on the column with the driver's input at the steering wheel. In this assembly, the electronic power steering module is incorporated with the motor and will receive inputs from different sensors on the smaller pins located here on this connector. And then it will receive higher amperage power and ground from power distribution on the larger terminals here. And then by receiving the higher amperage power and ground, it can then output a command to route that power from that module assembly into the electronic motor. With electronic power steering systems, it's going to be controlled by a control unit, an electronic control unit such as the electronic power steering, electronic control unit, or the EPS ECU. The ECU is going to receive inputs from a number of different areas, process that information, and then command an output to the electronic power steering motor. Some of those inputs can include steering angle sensor, battery power and ground, torque sensor on the steering column. It may have a high voltage supply to it, vehicle speed sensor or wheel speed sensors calculating vehicle speed, controller area network bus, all the other different modules that may communicate and have similar information that would be pertinent for the EPS ECU to receive and interpret, such as vehicle stability and anti-lock braking systems. As the electronic power steering motor is being commanded to provide variable assist left or right, there's going to be a feedback signal coming back from the EPS motor in the EPS motor rotation sensor. So there is also going to be an input feeding back into the ECU while the operation of the EPS motor is occurring. Some of these systems can be on vehicles that are hybrids or standard internal combustion engine vehicles. If that's the case, they have a 12-volt supply. The power steering system may operate on 12 volts. The power steering system may operate on 45 volts, or it may operate on the high voltage on 288 volts. So the high voltage system may pertain only to the steering system, or the vehicle can be equipped with other high voltage systems like in an electric car or a hybrid vehicle. There isn't always going to be a high voltage supply. That high voltage may be a result of the DC to DC high voltage converter inside the EPS ECU. So depending on the system and depending on the vehicle and how the vehicle is set up and equipped, there may be a high voltage system incorporated into the inputs, or it may generate its own high voltage inside the EPS ECU. Now that high voltage could be 45 volts, it could be 288 volts, or any variation of high voltage configurations. And it can also operate on a 12-volt system depending on how the system is configured. Working on any high voltage system is going to involve a degree of safety, and precautions and safety measures should be followed through service information in order to prevent injury or damage to the system or to yourself. Next, we're going to use the MODIS scan tool to monitor this system on the Spark EV and determine what the system is monitoring and what it's controlling from inputs to outputs, and look at some more of the active controls with the graphs present in driving the vehicle. So we're back at this undisclosed location where we can experiment with some of the inputs and outputs of the electronic power steering on the Spark EV. I'll go over some of the specifics on the inputs on what we're able to access with the MODIS and discuss some of the features that we may not be able to see. So we are working with the MODIS Ultra, and we're working on the power steering control module. We're going to go into the data display and read the data. So the first thing that we see at the top of the list is vehicle speed in miles per hour. That's our first input. Then we have battery voltage, which is in the 12.6 to 14 range. So this is a low voltage system. I'm not sure what the electronic power steering motor is using as far as voltage goes, but I would likely assume that it is higher than 12 volts. It's a very small vehicle, it's a full electric, so it may be using 12 volts, but that is not information that we have available on the MODIS. Next is steering wheel angle, steering input torque, calculated system temperature, and then back at vehicle speed in miles per hour. This is where we might have limited information using an aftermarket scan tool. We can read some of the data, just not all of it. And if we were to use a factory scan tool for a Chevrolet, this would likely have more inputs and functional tests available to us. But with the equipment that we're using, we'll work with the inputs that we have. So for starters, more assist is going to be needed at lower speeds. We're completely stopped right now, indicated by the 0 miles per hour on vehicle speed. And as I turn the steering wheel, watch the steering wheel angle and the steering wheel input torque change values. And I'm holding the wheel in a turn position. And as I release a little bit and add a little bit more torque, you can see that changing down here. And the steering wheel angle changing as well. I can go further. I can go back to center. And if I go the opposite direction, you can see the steering input torque graph goes the opposite direction. Do the same thing with the torque change on it as I move it back and forth. Since I'm in a parking lot, I'm going to start from a straight ahead position down one of the aisles and then turn into a parking spot and park the vehicle. Then we'll look at the data from the input and see what everything is doing, what the module is reading. So we're going to be traveling at low speeds with a lot of steering wheel angle. So the torque should be high on the steering wheel and the power steering assist should provide most assist at that time. Okay, here we go. Hit the brakes and turning into the parking spot. Point the wheel straight. Okay, we're parked. So looking at the first input, vehicle speed, 0 is the minimum, 13 was the maximum, 13 miles per hour, and that's reflected on the graph. So we started from a stop, increased our speed, slowed down, turned into the parking space, and stopped. Battery voltage had a little bit of fluctuation at 0.3 of a volt from 12.4 to 12.7, minimum to maximum. Steering wheel angle, making a right turn into the parking spot, is reflected by this increase value here. And then returning the wheel back to the straight ahead position here on the downhill side. Steering torque input. It was 0 when we were going straight. and this is in Newton meters. Steering torque input in Newton meters. Our units are right here. And it was 0, and then we turned into the parking space, and while the wheel was turned, there was no additional torque on it. The torque value didn't change. It stayed in position, so it remained constant. And then turning the wheel back a little beyond and then back to center. Since we're limited on what we can observe through the module for the electronic power steering assist system, I will be doing a lane change at about 50 miles an hour if I can get to 50 on the expressway here. As I do this, we can expect to see very little change in the steering wheel angle compared to the parking lot maneuver, and possibly less torque on the steering. So I'm just here waiting for the traffic light to change, and then I will do that test with the Modus monitoring what I'm doing, and I'll record and snapshot the data. Then we can review it when I'm done. All right, we're going at about 50 miles an hour. .4 miles an hour, and lane change. Wow, pretty exciting stuff. Data has been paused. We'll pull off and we'll review it. Vehicle speed, minimum 51, maximum 58. Stopped recording at 55. Battery voltage had 1/10 of a volt fluctuation. Steering wheel angle, here's where we see. Cruising straight, made the lane change to the right, turned back into the lane once the lane change was complete, and then straighten the steering wheel to correct for lane position and maintain straight with minor corrections. And our steering wheel torque, input torque, is just a value of 1 or 2 Newton meters. So same as in the parking lot. So no change on the input torque to the steering system. And I'm guessing since this is a very small electric vehicle, more on the budget side of electric vehicles, that the system is very basic. That there isn't a lot of different scales in which it's going to vary the power steering. It's either going to assist or not. And based off of that, it's using the steering input torque to determine how much force to supply to the steering gear itself. And in this case, it didn't make a difference whether or not we were turning into a parking lot at low speeds or making a lane change at high speeds. It still reads the maximum torque input at 2 Newton meters. Ideally, we should use a factory scan tool to see if there's more information available out of the module. Also, using a different electric vehicle or a vehicle with a different electronic power steering assist system would be able to give us more information than we are able to read with the Modus on the 2016 Spark EV. Sometimes you're limited by the scan tool, sometimes you're limited by the vehicle. This is an economy style electric vehicle, so there may not be very many things involved with the electric power steering assist systems that other vehicles might have. So, this has been Electronic Power Steering Assist. Thank you.